Hello everybody, I hope you're all doing well and hope you're all eager to try question number 13 on our 2008 Fermat paper. Let's dive in and take a look. In the diagram, the circles with centers P, Q, and R, put a little Oxford comma there, have radii 3, 2, and 1 respectively. I smell a 3, 4, 5 triangle, but that's because I've been doing a lot of these contests for a long time. So 3, 2, and 1 respectively. Each triangle touches the other two as shown, so they're tangent to one another. The area of triangle PQR is. Okay, so we've got some small circles. This one's going to have radius 1 and 1. Doesn't really matter, but we'll say 2 and 2, 3 and 3. And so what have we got here? We've got a triangle with sides 3, 4, and 5. And so this is actually going to be a nice little right angle triangle. It's quite nice. But let's write this up a little bit in our notebook. No particular reason we have to. I just like writing all these things down. But as soon as you get an answer, of course, you can always bubble in and move on. But I'm trying to present rather than just write contests. I think this was an R. This one's P. And this one's Q. And because they are tangent, we can connect up their radii, and they'll form little right angles, so they'll form straight lines, which is sort of a little bit of circle geometry that is necessary to do the problem and tends to get overlooked, but we put our, let's say 2, 2, 3, 3, same as I drew on the actual contest paper, but now what have we got? We've got a 3, 4, 5 triangle, which hopefully you recognize as the side lengths of a right angle triangle. If not, it is the Fermat paper, so you could use some trigonometry to figure out the area of this, or even just to figure out that you do have a right angle here. But yeah, 3 squared plus 4 squared is 5 squared. 9 plus 16 is 25. So this is a right angle triangle. If you didn't make this connection, you could, of course, do something like Heron's theorem, which says if you know the side lengths of a triangle, you can figure out the area. But we don't need that as long as we're aware of Pythagorean triples. And you should know at least the first few Pythagorean triples. They're always good to know. But our area here is then going to be 1/2 base times height. And because we've got a nice little right angle, we can have a base of 3 and a height of 4. And this gives me an area of 6. Okay, and 6 is one of our answers. That's B. Now, if you don't know Heron's formula, I'll just briefly mention it in case you are looking for ways to do this question when you're not lucky enough to have right angles here. Just because you've got 3 mutually tangent circles does not mean you'll get right angles here. But usually the 1, 2, well, always the 1, 2, and 3 will give that to you, give you a 3, 4, 5 triangle. But if we define S to be A plus B plus C over 2, this is sometimes called the semi-perimeter. Another calculation you can make is area is the square root of S, S minus A, S minus B, S minus C. I can't remember if there's a 1/2 or something in front. So let's just quickly try it out with these numbers. So 3, 4, and 5. That adds up to 12, so it's going to be 6. So we'll get square root of 6 times 6 minus 3 is 3, times 6 minus 4 is 2, times 6 minus 5 is 1. Square root of 36 is going to be 6. So yeah, we don't. This is Heron's formula. There isn't anything I needed to add on to the front of that. Okay. So, fantastic. There we go. 6 either way, but I do encourage you guys to know your Pythagorean triples, to be able to recall them nice and quickly and say, aha, right angle triangle, this simplifies my calculations. Because I think at this point, in terms of doing contests, you should likely know your Pythagorean triples. Some other nice triangles would be the 5, 7, 8 gives you a 60 degrees. There's a triangle like that. Obviously, I don't remember it. So we end the video with sort of petering out. But I will see you guys in the next video for question number 14. Until then, take care.